Okay, we're on to question 6 for the DEB mock papers of 2020, and the start of question 6 is a proof by induction. And it says prove by induction that A times AR times AR squared, so on, all these ratios is equal to this. And you can see it's the sum of a geometric series. So you have to prove this by induction, where R can't be equal to 1, because if that was true, then we'd be dividing by 0. So that's the only reason you have that. It's important to note what these symbols are telling you. Proofs by inductions are always a 3-step process. So regardless if you fear these or not, you should always stick to the 3 steps. Step 1 is the base case. It's basically put in the smallest value you can for n. So if we think about that, what does actually n stands for? Well, it stands for each term. N would be 1 for the first term, n would be 2 for the second term, and so on and so on. So you can actually see that if you were talking about an n of 1, it'd be replacing n by 1. That'd give you a times r to 1 minus 1. That'd be r to the power of 0, which would go up to 1. So you're just left with a. That's why you just have an a on its own at the front. It's technically a times r to the 0. So for the smallest value of n, that's literally the addition of the first term. Now we know that the first term, when we add up all the terms and just the first term basically on its own, add it to itself, well, just add it, is just a. So what happens if we replace n by 1? So does it work for that? Well, a times 1 minus r to the 1 over 1 minus r, that is essentially a times 1 minus r over 1 minus r, and of course they cancel, leaving a. So we can see that if we sum the first terms, we should just get a. Step 2 is also very easy to do. There's no maths here. This is an assumption case, right? So the assumption. So this can be true for all your proof by inductions. So for our assumption, we're going to assume true for some n equals to k. So you may think, why am I replacing n by k? What difference does that make? Well, you're not. N stands for any term, natural numbers, and that'll be important in a minute. K just means a specific term. So whatever n, we were talking about any term k. So we don't know which term it is, so just some nth term k. Well, if it's going to be true for some nth term k, we're saying that the first term plus the second term plus the next term, remember, if n is equal to 1, it goes to 0. If n is equal to 2, it goes 2 minus 1, which leaves you an r. If n goes to 3, it's 3 minus 1, which goes to here. All the way up to plus some kth term, a times r, and replacing n by k, k minus 1. So all the way up as far as there, that's up to the kth term. That should be equal to a times 1 minus r to the k over 1 minus r. Now, that assumption is going to be important in the next part. Step 3. This is your proof essentially here. We're going to prove it true for the term just above that. Well, what's the term above k? It's the term k plus another one up. So we're going to have to prove it true for this k plus 1 term. So that says that a plus a times r plus a times r squared up as far as a times r to the kth term, which is k minus 1, because remember we're just replacing the n by k. Now what happens if we replace n by k plus 1? Well, that gives us a times r to k plus 1 minus 1, and of course that's just k. If that's true, well then that should all be equal to a times 1 minus r. Remember, we're in the k plus 1 term now, to here, all over 1 minus r. Now, the big step here in this series, proofs for induction, is what we're going to do is we're going to just look at this left-hand side for a minute. If we look at our assumption says that all these terms up as far as this section here is equal to this stuff. What I want to do is, I want to look at all this stuff here, and I want to replace it by this. So we're going to say, okay, we're going to take out all that stuff in our proof. And we're going to say we know from our assumption that it should be equal to this. So that's a times 1 minus r to the k over 1 minus r, and then plus an a times r to the k, because that's that stuff out there that still has to go in there. Is that going to be the same as the right hand side here? Well, hopefully. So maybe if I put this up here so you can see it, and we'll say, alright, so look at this side here. Well, how can I add these together? Well, I can't do anything here yet because I don't have a common denominator. Remember, I'm trying to get it to look like this side over here. So I'll stick with this term for a minute. Over 1 minus r. Now, how do I make this look like something over 1 minus r? Well, I'll just multiply it above and below by 1 minus r. If that's true, if we do that, that's just like multiplying it by 1. It doesn't do anything to it. You may understand that, but in case you're wondering, something over itself is 1. So multiplying this by 1 is not going to change the properties of it, but it'll just change the look of it. And this stuff now is still going to be the same. And this stuff now is going to be this. So that's a r to the k times 1 is just a r to the k. Now, a r to the k times minus r. Well, it's going to change it to a minus. And still going to have an a, and I'm going to have r to the k times r. Remember, we would add the powers there. It's essentially to the power of 1. So that's going to be ar to the k plus 1. So this multiplied by this gives us this stuff here. Because the powers add. Like if I had x cubed times x cubed, that'd be x to the power of 6. I'd add the 3 and the 3, so I'm adding the k and the 1 to give me this. And that's all over just 1 minus r. Now remember, I'm trying to get it still to look like this stuff over here. Now these two things have the same denominator, which is this stuff here. And this stuff here is the same denominator. So we can actually add the whole top row and put them over the one denominator. So we can say a times 1 minus r to the k plus a r to the k minus a r to the k plus 1. And that's all over a 1 minus r. Now again, we're trying to get it to look like this stuff here. So, actually multiplying this a here, what do I get? Well, we'll see that we have a, and then a times minus r to the k, a r to the k, plus a r to the k minus a r to the k plus 1. That's all over 1 minus r. Now hopefully you should see these two terms cancel. And I'm left with a minus a r to the k plus 1 all over 1 minus r. And of course if I factor out an a, I get a 1 minus r to the k plus 1 all over 1 minus r. And yeah, that's what we wanted to get to. We actually wanted to get to this term here. And if we look now what we have, I actually have this left hand side here being the exact same as the right hand side over there after a small manipulation. It is tough, but practice will get you there with them. Proof by inductions are never answered that well from my experience correct in exams. So I mean, they just take practice. You need to stick with them. In general, the same type of ones come up a lot. So what we can say now is, since it's true for the k plus 1, since the proposition is true for that, and since, say, true for n is equal to 1, you can say sometime therefore is true for any n, an element of the natural numbers, because they're terms, so it's the first, second, third. You wouldn't know the 1.5 term. So there's a nice fancy sentence you can learn it off, but every proof induction has to finish like that. And that's that one done. Okay, on to question 6, part B. It says the sum of the first 5 terms of some geometric series is equal to 5, and the sum of the next 5 terms of the same geometric series is equal to 160. This is the formula for the geometric series given in your logbook. look at the first line, what it tells us. The first 5 terms added together is 5. So we can say S of 5 is equal to sum A minus, 1 minus R to the 5, because it's the first 5 terms, over 1 minus R, except we know that's equal to 5. So the next 5 terms equals to 60, so maybe it's a little tricky in the way it's written, but essentially now we're going to have an S of 10, because of the first 5 and the next 5, that's 10 terms. We know that the next 5 added together is 160. We know the first 5 added together is 5. Therefore the first 10 should add to 165. So again, the first 5 add to 5, the next 5 add to 160, so the first 10 then must add to 165. That's the first hurdle you had to get over. That's A, 1 minus R, now we're talking about 10 terms, and that's all over 1 minus R is equal to 165. Okay, so from that we need to figure out a couple of things. Now we need to figure out A and we need to figure out R. So if we can figure out either A or R, like they're like simultaneous equations, I suppose. So a couple of ways to do this. One way I can think of doing it is, we know that R and A is the same in both. A small rearrangement on each of these would say this. So A times 1 minus R to the 5 still on top. But I'm going to switch places with these two. So I'm going to bring the 5 down here. I'm going to bring the 1 minus R up to there. Literally just rearranged it. I'm going to do the exact same thing here. I'm going to say A 1 minus R to the 10 over 165 is equal to 1 minus R. Now remember, R is the same for both equations. 1 is a number the same in both equations. If these two things are equal to 1 minus R, it's safe to say they're both equal to each other. They both must be the same because they're both equal to the same thing. So we can say this then. A 1 minus R to the 5 over 5 equals to A 1 minus R to the 10 over 165. Now we have A on both sides, so they're the same in both, so that can go, and we can definitely try and solve this for R. If this was X, we'd bring all the X's to one side, so let's treat it the same as the X. Let's bring the R's to one side, so let's get this guy over here. The only way he can come over here is down underneath and get rid of this 5 up to here. So my next line would look like this: 1 minus R to the 5 over 1 minus R to the 10, like so. Okay, and that's going to be equal to 5 over 165, like this. Okay, so we're down to here so far. So how can we start cancelling off some stuff here? What can we do? Well, I don't know what you might like to do here. There's a couple of different ways we can probably go about this. We could try and rationalize it some way here and make it a bit better. One way I thought of doing it from the minus here is, because 1 is a square, perfect square, this is what I did. So I'd say 1 minus R to the 5 on top. Now, let's go and put a circle around here. R to the 10. R to the 10 can be written like this: R to the 5 squared. So, be comfortable with that. R to the 5 squared, that's R to the 10. So actually, I can do the bottom like this: 1 minus R5 squared, still equal to this stuff over here. That definitely goes into something there, so I think that goes like 1 over 30 and 333. Now actually, if we look now at the bottom part, I hope you might see that's the difference of two squares. So we can actually stick on the top as 1 minus R to the 5. But now the bottom, that's 1 minus R to the 5 and 1 plus R to the 5 equals to 1 over 33. Now you get this. So they cancel and we're left with 1 over 1 plus R to the 5 equals 1 over 33. Now I can just switch these around, but of course the ones now don't make a difference. 1 over something is equal to 1 over something. The only way that can be true is if these two things are equal to each other. So that means essentially I have 1 plus R to the 5 is equal to 33. meaning r to the 5 is equal to 33 minus 1, 32. And that says that the cube root of 32, that should be 2. Yeah, because 2 to the power of 5 is 32. Therefore, r must be equal to 2. And of course, what I didn't do here is this, the cube root of 32, just to get rid of that 5. So we have actually r is equal to 2. Lovely. So if r is equal to 2, it should be fairly easy to find a. We can just sub this r is equal to 2 into one of the original equations, much like a simultaneous equation. So we can say this. We can say we have S5 is equal to A1 minus, and now r is going to be 2 to the 5 all over 1 minus r, which is 2, and that was equal to 5. So this ends up being A1 minus 2 to the 5, now is 32, all over minus 1, and that's equal to 5. So now we know A times minus 31 is equal to, looks to be minus 5. Therefore, A must be equal to minus 5 over minus 31. And of course, that's just 5 over 31. That's that. So we're on to the final part, and for the final part it says find the smallest value for n where the series is greater than 10,000. So I had accidentally put in 1,000 here, so I changed it here. So when does the series get bigger than 10,000? Remember, we figured out from part 1 that if you add the first 10 terms together you get 165. So since the ratio is bigger than 2, this thing's going to keep getting bigger. So what term do you get to when you add all the terms up to that term? Does it break through the 10,000 barrier? So for our specific sequence, we want to know when does it get bigger, or series, when does it get bigger than 10,000? So let's fill in what we have. So we have an A of 5 over 31, and we have our, multiply that by 1 minus r, which we now know to be 2, to the n, over 1 minus r, which we know to be 2. When is this stuff true? So we'll do this maybe. 5 times 1 minus 2 to the n we leave alone. 1 minus 2 is minus 1, so that's 31 times this stuff is minus 31, because of course 1 minus 2 is minus 1. It's minus, and it is greater than 10,000. Now we have a negative sign here, so super careful messing around with negative signs and inequalities like this. First thing I'm going to do is I'm going to divide across by 5. That gets rid of this 5 and makes the right hand side 200. So remember, I'm dividing across by 5. That's giving me this, or 2,000. Okay, what's the next thing I'll do? Well, now I'm going to multiply across by minus 31, but where is the major problem here? Well, when we multiply across or divide by a negative, we must flip the inequality, so just be careful there. So what do we have? 2,000 multiplied by minus 31. That gives us minus 62,000. Now I'm down to here, so I'm getting close. So I have just 1 minus 2n, so I can bring over that 1, it becomes minus again. Minus 62,001. Because it's minus 1, it makes it back the way a bit bigger. Now I can change the signs, but again, since I'm changing the signs, I have to also change the inequality. So that's now I have 2 to the n greater than 62,001. How do I bring that n down? Well, it's going to be the log base 2 of both sides, and of course log base 2 of this side is going to get rid of this, and we're going to be left with n greater than the log base 2 of the other side, which we also have to do. So a log base 2 of 62001 base 2 of 62001. When we do that, we get n must be greater than 15.92. So that means somewhere between the 15th, after the 15th term, you get bigger than 10,000 for n. So what's the next term? What's the closest term there? Well, we have to go to the 16th term. Obviously, when you get to the 15th term, You're not quite there at 10,000. It says it's like 15.92 will get you on the money at 10,000, but no, we can either have the 15 term or the 16 term. 15 term doesn't get us there, so n for this must be equal to 16. So that is the smallest value for n before we actually break the 10,000 barrier. That's question 6 done.